A bit of quick revision on what we said in the last lesson. If you remember, int a, if you declare int a, then a is a variable. It occupies 2 memory locations. If you remember, a occupies 2 memory locations because you have declared it as int a. Similarly, if you declare float a, what does it occupy? It occupies 4 memory locations. When you write float a occupies 4 memory locations. 1, then this memory location, this memory location, then third memory location like this, and fourth memory location when you write float a. Similarly, if you write char a, this is the new data type we learned in the last class, char a, then a occupies 1 memory location only. That means 1 memory location, how many bits is it? 8 bits. 1 memory location, 8 bits. 2 memory locations, 16 bits. 4 memory locations, 8 into 4, 32 bits. However, 1 memory location, 8 bits or 8 binary digits. What are they then? See, the weights if you assign 8, 4, 2, 1. Weights of 4 bits, 1, 2, 4, 8. 1, 2, 3, 4, 4 bits, 8. The next memory location, the weight is 16. The next bit, the weight is 16. The next bit weight is 32. The next bit weight is 64. The next bit the weight is 128. Is right so? So see how many bits? 1, 2, 3, 4, 5, 6, 7, 8, 8 bits. Now this is a character. That means any character, any integer obviously is represented by bits within a memory. Now in a character then, what is the lowest representation possible? The lowest representation possible is all these 8 bits 0. Is not so? All these 8 bits can be 0, the lowest number possible. Is not so? What does this mean? All 8 bits 0 means the number is 0. Similarly, if you think of, then it continues. Next number is all zeros, last bit 1. Next number is all zeros, last 2 bits 1, 0. In this way, what is the highest representation possible? All bits 1. That is 1, 1, 1, 1, followed by 1, 1, 1, 1. That is all 8 bits can be 1. That is the highest representation possible. Now what is this number? This number is 255. That's why we say, using ASCII, the American Standard Code of Information Interchange, all these numbers 0 to 255, they represent some character or the other. 0 does represent some character. Also 255 does represent some character. Is not so? Similarly, if I continue, say in between is 65. 65 represents some character. Which character does it represent? It represents capital A. Similarly, if I continue, 66 represents what? Capital B. In this way, if you continue, 67 represents capital C, and so on. 90 represents capital Z. You continue, 97 represents small a. Small a. 98 represents small b. In this way, if you continue, 122, that represents small z, and so on. There are so many other representations possible. Is not so? In between lies 48 maybe. In between lies 48. What does 48 represent? 48 represents 0, the character 0, not the integer 0. The character 0 is represented by 48. So this is 48. In this way, 49 represents 1, 50 represents 2, and so on. These are the representations. So if you remember, when we are writing character A is equal to 97 and then trying to print %C, if you remember %C and A, then this will definitely print the character A itself. Is not it so? Because 97 represents small a. If you represent this, if you write 98, then definitely this should print small b. Is not it so? Because the characters are all represented by these numbers. Now see what happens. I write this thing, do this little revision, and then show you something very new. Character A equal to 98, and then I printf %C followed by A. What should it print? It should print small b, because 98 is the representation of small b. So let me print that. Oh, firstly let me comment out this whole portion. This is very important that you comment out before running anything, all these portions that you don't need. Okay, so there is one small thing. This also gets inside the comment. I need to comment out that 1111, all that portion needs to be commented out. So this is now commented out. Now character A equal to 98, I printf %C A. What should it print? Definitely it should print B, because 98 is the representation of small b. Alt enter C small b. What if I take it as 122? 122 is the representation of what? Small z. So it should print small z. In fact, I had shown you with all numbers possible 0 to 255, you had seen it. In this way 65 is capital A. Is not it so? If I write 65, this should now print how much? This should print capital A. Is not it so? Let me run it. Alt enter. Yes, capital A. In this way you are printing it. Will not make too much of a difference if I represent this character and make it int. Sorry, if I change this character, and make it integer, should not make too much of a difference, because ultimately 65 is present within A. If you print it as a character, definitely it will print capital A itself. Run it and see for yourself. Yes, capital A it is. Capital A it is printing. So integer does not make too much of a difference. Suppose it is 97, it should print small a itself, even if I represent it by integer. Now one very interesting thing that I want to show you over here before continuing, I change this 97 and make it 353. %C is not possible, because if you remember, the representation of characters are from 0 to 255. See this? Just a while back I explained. 0 to 255 are the representations of the character, because character is represented in 8 bits, and in 8 bits what is possible is between 0 to 255. So 0 to 255 is are the representations of the characters. If I write 353 and try to print it as %C, should it print anything at all? It should not, because 353 is no character at all. But still let me run it and see. Alt enter. See, it prints small a. What happened? Small a is 97. How come suddenly 353 prints small a? Very odd. Suppose I take 354. Sorry, 354. Let me run it. Small b. Why? 353 small a, 354 small b. Why? Small a was 97, small b was 98, and so on. Is not so? Suppose you suddenly take 355. What should it print? It should print small c. Is not so? What do you make out of it? If I take 321, what should it print? Capital A. But capital A was 65. How come suddenly 321 is printing capital A? This I want to explain to you now. See, when you write int a equal to say 4, You know an integer is represented using 16 bits. So yes, definitely 128, then 64, then 32, then 16, then 8, then 4, then 2, then 1. These are 8 bits, no doubt. But prior to that, 16 bits makes an integer. So what are the weights prior to that? I want to explain this now. It is 255 which is present, 255. Prior to 255, what is present? 256, not 255. 256 is the weight just before 128. What is prior to 256? 512. What is prior to 512? 1024. Is not so? What is prior to 1024? Prior to 1024 is 2048. Is not so? How many bits does it make already? It makes, this is 8 plus 4, 12. What is prior to 2048? It is 4096. What is prior to 4096? It is 8192. What is prior to 8192? It is 16384. Please check this. Is not so? How many bits does it make now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is not so? So what is prior to 16384? I count once more. 1, 2, 3, 4. 4 bits. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I have written 15 bits. What is prior to that? Prior to that is not a weight. It is the sign. That is, 0 over here means plus, 1 over here means minus, because an integer can be positive or negative, which a character cannot be. In case of a character, we never needed the sign bit, because after all, characters does not need any sign. Characters are not signed numbers. Characters are maybe A, B. These are not signed, does not need a sign. But integer needs one extra bit, which is the sign bit. So when you write int a equal to 4, it is a positive number. This is 0. If you write int a equal to minus 4, this is 1. Now what is 4? 4 can be represented as 1, 0, 0. So prior to that, you will agree with me, all bits should be 0 itself, does not have any weight at all. If I want to represent 4, then 4 is represented like this. All zeros and then ending with a 1, 0, 0 at the end. That is 4. Is not so? This is 1, 0, 0 at the end. This is how int a is represented. But this is 16 bits. But the 16 bits on memory are like this, 2 memory locations. How is 4 represented? See this, very important. See, these are the last 8 bits. These are the last 8 bits. Is not so? These last 8 bits are stored here. 0, 0, 0, 0, 0, 1, 0, 0. The last 8 bits are stored in the first memory location corresponding to A. Int A will mean 2 memory locations, but the last 8 bits are stored here. And the upper 8 bits, that is all zeros, in case of this where you write A equal to 4, is stored over here. Do you get it? Now say suppose you write, say 259. How do you represent 259? Within 259, first you can fit 256. Is not so? In 259, firstly you can fit 256. So now you are writing int a not equal to 4, but int a equal to 259. How do you represent 259? Firstly, 256 can fit in 259, is not it so? 128 cannot fit, so it is 0 itself. 64 cannot fit any further because after fitting 256, only 3 is left to be fitted. You have already fitted 256, only 3 is left to be fitted in 259. So 128 does not fit, 64 does not fit, 32 does not fit, 16 does not fit, 8 does not fit, 4 also does not fit. 3 is left, so a 2 fits. A 2 fits means you have already fitted 256 and 258, only a 1 is left which you fit over here. So this is the representation of 259. Now out of this 259, what are the last 8 bits? Check out 1, 2, 3, 4, 5, 6, 7 and 8. Last 8 bits. So don't you think that the last 8 bits are this? The last 8 bits are stored over here and the upper 8 bits are stored in the next memory location. That is the rule. That is the rule of C programming. That is how it is done. So if you take this upper 8 bits, see these are the upper 8 bits. Check out 1, 2, 3, 4, 5, 6, 7 and 8. These upper 8 bits, which is all 0 followed by a last 1, is stored over here when you write int a equal to 259. That is the rule how it is done. Had it been 771, then, now I am not saying 259 but 771, check this. 771, what will happen? In 771, all these numbers do not fit. Even 10224 does not fit in 771. But yes, 512 fits. Now after fitting 512, how much is left out? You can say left out portion is 259. See, 512 plus 259 makes it 771. So you can definitely fit 256. 512 and 256 makes it how much? 768. You are left out with 3. So you can fit a 2 and a 1. So what is the representation of 771? These last 8 bits still remain the same. Is not it so? But the upper 8 bits, it becomes 1 1 over here. Is not this the representation of 771? This is how 771 is represented when you write int a equal to 771. Now I will show you one very interesting thing now. When you are writing int a equal to 97, which in character version is the representation of the character C. Now what is 97? I will again try to fit over here. What is 97? 512 does not fit in 97. 256 does not fit in 97. 128 does not fit in 97. But yes, 64 does. 64 fits in 97. Does a 32 fit anymore? Yes, because 64 and 32 makes it 96. After writing 64, you are left with 33. So yes, 32 does fit. But after fitting the 32, you are only left with 1. 16 does not fit, 8 does not fit, 4 does not fit, 2 does not fit. But a 1 fits. So the representation of 97 is this only. If you write int a equal to 97, if you write int a equal to 97, then the representation will be the last 8 bits are this. The representation of 97. So the last 8 bits will become 0, 1, 1 followed by 0, 0, 0, 0, 1. That is what is int a equal to 97. When you write int a equal to 97, that is how it is. The first 8 bits, these are represented. Now the upper 8 bits which are represented in the next memory location, you see are all zeros. This is how you represent 97. But in terms of character, this representation is the representation of small a because it is 97. Now instead of writing int a, when you write int a equal to 97 and you write printf %c followed by a, you know that what is printed is the character a. The character a is printed, is not it so? Now what if you write the same thing, int a equal to 353, and you are trying to print printf %ca, %ca, what will happen? You have seen while running that again the small a is printed. Why? That was the question. You check out why. Because 353 means, what is the representation? All these numbers do not fit. Even 512 does not fit in 353, but a 256 does. After fitting 256, you cannot fit 128, because after fitting 256 in 353, you are left with 97. So 128 does not fit, but a 64 fits, 32 fits, and this 1 fits. So this is what is 353. After writing 256, 97 has to be fitted. So this is 97. So what is the representation of 353 within the computer memory? The last 8 bits are stored in the upper location. So this location contains the same thing. These locations contain the same thing. 0, 1, 1, 0, 0, 0, 0, 1. Same thing. And to this number, the upper 8 bits are this last bit 256. These are the lower 8 bits starting from 128. So up to 256 are the upper 8 bits. The last bit is 1. All others are 0. When you are writing 353, it is represented within the computer memory like this. The upper 8 bits are 97 and these just takes the 256. This is how it is represented. Now this is the representation of what in terms of a character? This is the representation of small a, because this is 97. So when you are printing %ca, automatically it thinks that it is printing a character. If it is printing a character, %c means it is printing a character. If it is printing a character, then from a, how many memory locations should it take? Character means 1 memory location over here. So definitely it takes the upper memory location, this memory location a. 1 memory location it takes. What does it contain? It contains 97. Yes, it is 353, but 353 is because of this extra 1 which is in the next memory location, 256 over here. But this is the representation of small a, 97. So here it prints a. Do you understand? Even if you change this bit, had this bit changed and made it 1. What is this? This is 1 means this is 1. This is 1 means an extra 512 added. See what is this? 512 and 256 makes it 768. 768 plus 64, 32, 1, that is 97. 768 plus 97 makes it how much? 865. Is not it so? 865. So what if I change this 353 and make it 865? Let me check once. Say this is 865. What should happen? Even if you are writing 865, remember this is 1, but this part remains unchanged. This is the representation of small a. So what should it print? Should not it print small a again? Alt R, enter. Yes, it is printing small a. Like that, 866 should again print small b. It's not so. Because 866 is basically 1 more, that is 866 is firstly 512, then 256 makes it 768. You are writing 866, so 64, 32, 96 fitted, you are left with only 4. Because 768 plus, this is 768, plus 64 and 32, not 98, 2 left out, sorry. 512 and 256 makes it 768. 768 plus 96, 64 and 32 makes it how much? 864. You are left with only 2, that is 866. Is not it so? Now this representation will mean that 512 and 256, these are 1 1. Now look at the last 8 bits, 0 1 1 0 0 0 1 0, not 0 1 but 1 0. What is this? What are these 8 bits? Check out what are these 8 bits. 64, 32 and 2, that is 98. 98 is the representation of what? Small b. That is why you are printing, you are actually taking 866, but it is printing small b itself. I think you understand this. Now this is interesting. If you write this as CAD A equal to 866, then what will happen? No change, still B, because CAD A 866 means it is just neglecting the upper 8 bits. It is only storing the last 8 bits in the first memory location, because CAD A will mean you are printing the last, you are just taking the last 8 bits of 866 in the first upper memory location. So what is that? 98, it prints B. It hardly matters. Is not it so? Do you understand? Even if you print it as a %D, you are writing CAD A equal to 866. If you print it as a %D, what will be printed? It will print 98. See, because when you are writing CAD A equal to 866, 866 is represented like this, no doubt. But you have taken CAD A, so only the last 8 memory locations, only the last 8 bits are stored in the only one memory location that is allocated. When you are writing CAD A equal to 866, it is allocated only one memory location, allocating only one memory location, that is 8 bits. So when you are writing CAD A, it is allocating only one memory location, 8 bits. You are writing CAD A equal to 866. So it is taking the last 8 bits and storing this 98 over here. And that's why when you are printing it, even as an integer, it is printing 98. But if you write this as int A, definitely the first old program, yes, 866 will be printed now. Because int A equal to 866, print a %DA. It is an integer, you are printing the integer. You change this to character, it will only allocate one memory location and it will print the last 8 bits. The representation of the last 8 bits, 98. You print that as %C, it will print small b itself. Now in this way, you know, if you write it as say 866, instead of 866 you take 1 and print A, what will it print? It will print the character representation of 1. What is the representation of 1? Check out. It's a smiling face. A smiling face character has got the integer 1. 2. Again a smiling face. A better smiling face. In the it's a better looking smiling face maybe. So if you are taking 3, then a sign of heart. If you are taking 4, then maybe some other similar diamond shapes thing. So you understand this? Character equal to 1, 2, 3, 4, whatever you print in this way, maybe 65. Again, capital A. Is not it so? In this way, 97, small a. That is why in my last program, by shifting by 32, you just change the cases. If it was 97, 97 minus 32 made it 65, the capital case. If it was 65, 65 plus 32, 97 made it the small case. So I think you understand all this. Now what if one program to end this entire discussion? The program is fill up the screen with smiling faces. Fill up the screen with smiling faces. What will you do? You know 2 is a representation of a smiling face. 2, if you run this program, 2, see 2 is a smiling face. So you want to fill up your screen with this smiling face. What to do? You write char a equal to 2. Now you write for I equal to 0. I less than, maybe 100, I plus plus, you write printf %ca. What will happen? Small a will be printed 100 times. Now what is small a? Small a is 2. So representation of 2 is a smiling face. So the smiling face character will be printed 100 times. One thing you remember over here, even if you over here make int a equal to 2, it hardly makes any difference. Int a equal to 2 will allocate 2 memory locations. But the upper memory location will contain 2 and the lower memory location will contain all zeros filled up. Because 2 is all zeros in the first 8 bits and 0, 0, 0, 0, 0, 0, 1, 0 in the last 8 bits. So it is 2 in the upper memory location and all zeros in the next memory location. So when you print it as a character, it will take as 2 itself. It hardly matters. Same thing. However, printing %ca means you are trying to print this 2 as a character. How many times? 100 times. So 100 times 2 as a character will be printed. 2 as a character is a smiling face. So 100 times a smiling face will be printed. Alt R, enter. Undefined symbol I. Yes, I did not declare I. I must be declared as an integer. Int I should be declared. Anyway, let me run it. Alt R, enter. So 100 times this A or 2 as a character will be printed. 2 as a character is a smiling face. So 100 times the smiling face will be printed. 100 times the smiling face has been printed. Doesn't look too good. It's all white, 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 white. You may give a bit of space in between. It will look better. Between two smiling faces, a bit of space. This is better. It's not so, but 100 is nothing. You need to fill up the screen. Let's make it 200. Still it is nothing. Let's make it 800. A big jump. Quite enough. Now you can make it even 1000. So now it is better. The screen has been filled up with smiling faces. Is not so? So do you understand how to do it? Even if you would have done it with 1, 1 is also a smiling face, a different version of a smiling face. If you write carry equal to 1, now 1 will be printed, but yes, 1 will be printed as a character, not as an integer. As an integer, if you will print it, it will print 1 itself. 1, 1, 1, 1 and so on. So you are printing it as a character, means it will print a smiling face, many smiling faces, 1000 smiling faces. This is even better. Is not so? This representation of the smiling face looks better over here. So yes, this is a program to fill up the screen with a smiling face. So you can do similar programs with character. Maybe we will do 1 or 2 more programs with character. A little bit of more discussion with character before we go to a new concept called strings. You can take a bit of break and we'll come back. Thank you so much.